In this lecture, we're going to talk about different components of atomic spectrometers. I think you already well know that there are different types of atomic spectrometers based on their mode of operation. I think we've already talked about AAS, for example, which is based on absorption spectrometric kind of mode. You can also have emission atomic spectroscopy. And with that emission atomic spectroscopy, you can also have fluorescence, which is sort of a type of an emission spectrometer. Although it's not very, very common, with atomic spectroscopy, it's more common with molecular spectroscopy. But I'm gonna give you one example, at least, of an element, that tends to undergo fluorescence, although that's not very common. Only one element, which is typically mercury, but the other elements typically do not undergo fluorescence. So in essence, you've got only really one commercial type of atomic spectrometer that is based on fluorescence, and that is a mercury detection system. Now, it's not very common, to do phosphorescence, because of the reasons that I gave you before. If you look at the Jablonski diagram, that for you to do phosphorescence, you need to have intersystem crossing happening, and that's not very, very common, with elements. So I would say the two most common type of atomic spectrometers, of course, would be the absorption, which you guys have done in the lab, the AAS, but you can also do emission spectrometry, which is AES, atomic emission spectrometer, and with fluorescence, you can have a mercury detection system. So it's very important, to remember the components of these types of spectrometers, but also remember the configuration. For example, when you're doing absorption spectrometer, typically that is a configuration where the light source, it's in line with the detector. When you're doing atomic emission spectrometer, this is a configuration here where the source, is at right angles, to the detector. Now, of course, well, there are many applications, of atomic spectrometers, be it AES or AAS, which is principally, ability to analyze different types of elements in different types of matrices. You guys already did determination of copper in beer using AAS. You also determine different composition of metals in brass, for example, which is an alloy. You can also, do detection of metals in engine oil, used engine oil, very, very common type of way of determining, how well your engine is running just by looking, at the heavy metals that are present in the engine oil. You can look at, different types of nutrients, in soil, in fertilizers, in foods. But the key is, of course, we are dealing with elements in this case. Now, for the sake of your exams and so on, for you to really understand what's going on, you can be asked a question, such as this, design an instrument, possibly, for field applications, which is very, very highly sensitive. And so make sure you determine, which choice of component do you actually use, to build your system. And that is really the purpose of this lecture, to understand why do you use each particular component, that you integrate into your atomic spectrometer. Because who knows, of course, some of you may end up being hired, by instrument manufacturers, and you'll be able to, you will need to understand, the basis of every component that is typically used. So with atomic spectroscopies, of course, you need a component or a way to introduce your sample into the system. And as simple as it sounds, it very, very highly impacts your sensitivity. So the method of sample introduction that you use, highly impacts your sensitivity, but also, of course, it impacts, things like the sample throughput, how many samples can you run, in a minute? Again, the sample introduction technique, determines, sample throughput, how rapid, can you run the types of samples that you have. Equally, the type of sample introduction method you choose determine whether you can simply run a solution, or you can actually run a solid sample, meaning you don't need to prepare the sample for analysis, which helps you in terms of saving cost, saving time, and so on. Now, I'm gonna list, maybe 8 different sample introduction methods, and of course, for the sake of exams, it's important for you to be able to list them and explain, how they work. Now, one type of, sample introduction method, maybe the most common, is what you refer to as a pneumatic nebulization. And it can be used to introduce solutions, as well as slurries, as samples. Now, that is what you guys did in the lab, actually. You, with the AAS, you did pneumatic nebulization. And as the name suggests, pneumatic simply means pressure. So essentially, you're pressurizing, your sample solution, through the system. Now, another method, that you can use is what you refer to as ultrasonic nebulization. And this is a process, by which you can introduce a solution, and the solution impinges or hits a crystal that is vibrating. And because the crystal is vibrating, the solution splits into a mist. Because ideally, you want the sample to actually be converted, into a mist, that is transferred, into your atomizer. And I'm going to show you that in a later slide. Another type of, sample introduction method is a furnace, or what you refer to as electrothermal vaporization. And that is where you just simply have a furnace, a very small furnace actually, very similar to a GC injection pot. And then you have, you can introduce your solution, you can introduce even a liquid or even a solid, can actually be used, when you are using a furnace on electrothermal vaporization technique. Now, the other type of method of sample introduction is hydride generation, and I'm going to talk about it later on. But typically, you use it, for very specific types of elements. So it's very, very selective for hydride generating type of elements. And I'm going to show you, how to do that. Other methods, include, direct insertion, where you just simply take the sample and somehow, you introduce it, to the atomizer, maybe using even a spatula, and so forth. And of course, you can see that you can analyze, solids or powders, using that type of method. Another method is laser ablation, where typically you use a laser. And remember, how the laser is made. I think I described that previously when we are talking about different types of light sources. And laser, of course, stands for light amplification, stimulated emission, radiation. So it's an acronym, actually. So it's very, very energetic, meaning if at all you've got a sample, maybe you put it on a glass slide, you shine a laser on that glass slide, you get, the sample being ablated, to the atomizer. And of course, you can see with a laser ablation, you can analyze solids samples as well, which is very good because you don't need, to do dissolution, which takes a lot of time in the lab. Maybe the last type of, technique I'm gonna mention is a glow discharge sputtering, which is actually a lamp. And I'm gonna show you a slide later on this, where you just take an electrode, and you put your sample onto an electrode, and then you expose it to a fast atom moving beam, and it causes the sputtering or ablation of your analyte, and it goes to the atomizer. So with a pneumatic type of nebulization, you can use 4 different types of, or even 5 different types of pneumatic nebulizers. And as you can see, each one of these, can be fairly resistant to clogging, because one big problem, we have with nebulization is clogging. Clogging meaning, if at all you've got dissolved solids in solution, they tend, to clog, the orifice, that is being used, for the nebulization. But some of these, pneumatic nebulizers, as you can see, possibly, they've got different resistances, to the clogging effect. So one type of pneumatic nebulizer is what you call the high pressure gas flow, where you've got a pump, and the pump is pushing the solution, through a tube. And then you've got gas, that is moving around that tube. And because of that, you get, nebulization, or the spray of that solution into a mist. And in fact, what you refer to this really is what you call, I think, the Bernoulli effect. The Bernoulli effect, where you've got, a high pressure gas, revolving around a concentric tube. And because of that, you get a suction, taking place. So in actual fact, in this case, you don't really need a pump. Now, another type of, nebulization technique, pneumatic nebulizer, is where you've got, is what you call the cross flow. And the cross flow is where you've got the sample, and the sample is being pumped using a pump, and then you've got a high pressurized gas, colliding, with that solution. And of course, you can see that you end up, with a plume or a mist, that goes to the atomizer. And ideally, of course, the finer the mist, the better the atomization will be. So ideally, nebulization, we are looking to convert, the droplets. You're looking to convert the droplets really into a mist. That's what we are looking to do with nebulization. Now, the third type of pneumatic nebulizer here is what you refer to as a fritted disc. And as the name suggests, you've got the high pressure gas, that is going through a frit. And a frit, is just a material, that is porous. And then you've got the sample, that is being pumped, across that frit. And as you can imagine, there's a collision, between the high pressure gas and the solution flow. And of course, you get a mist, as well. Now, lastly, you've got the Barbington type of pneumatic nebulizer, where essentially you've got a ball or something that looks like a balloon, and you've got the high pressure gas, going through the balloon, and then you just prick the balloon, make a small hole, and as you can see, of course, the gas sort of, makes a plume, and you've got the sample, that is dropping or rolling, on the balloon or on the ball, and as it gets to the orifice, it gets pushed out and split into a mist. So you can see all those are examples of different types of pneumatic nebulizers. And as you can see, really, the Barbington, is the most resistant to clogging. Now, in our list, of different sample introduction methods, there is always a desire to multiplex, or have a system that performs more than one purpose. So if you are able, to have a system, that is able to introduce a sample, and yet the same system is doing the atomization, breaking, the mist into its component atoms, then, you've got a fairly better system, because you can miniaturize, your instrument. And one example, of a system that can actually do both sample introduction and atomization is what you refer to as a glow discharge. And this slide or this picture, shows you a picture of, the glow discharge lamp. Really, it's a lamp. And now what it is you got a cathode, And in the cathode, you coat it in the cathode, you coat it, with a sample of interest. And then you introduce, this cathode coated with a sample of interest, and you introduce it into a chamber, that is pressurized, containing argon gas at a pressure of around, 10 torr. And now, if at all you've got this sample in a cathode, you can simply short circuit it. If at all it's positively, the cathode is negatively charged, and then you've got an anode, which is positively charged. If you bring it into connection, you momentarily bring the two electrodes into contact. Essentially, you'll be short circuiting, the system. And as you short circuit the system, of course, you guys know that causes a spark, to happen. And if at all there's a spark, you get the sputtering, you get the sputtering really of this, of the sample, that is coated, and it gets sputtered, and you can cause atomization that way. All right. Now, another way that you can actually operate this system, equally is by applying a voltage, on this gas that is inside. And when you apply a voltage, say on the anode, it can cause, the ionization of the gas, or the argon gas. And so the argon gas, is ionized, to make the argon cations. And the argon cations, can be accelerated, to the negatively charged cathode, and that causes the sputtering effect. It's really what they call the first atom bombardment, and you got the argon gas, that is ionized and is being accelerated to the negatively charged cathode. And then there is an impingement, and that impingement, causes the ablation of your material as well. So you can see it's a combination, of sample introduction, but also atomization. Now, of course, whatever is atomized, can be detected either by atomic absorption. It can also be detected by atomic fluorescence, or it can be detected, by atomic mass spectrometer. So other type of specialized techniques, that again combine atomization and sample introduction methods, while at the same time being very good, for the analysis of solid samples, meaning you don't need to dissolve the sample, includes, the glow discharge, which I've talked about, in the previous slide. But you can also use a furnace. And as I said before, the furnace really is just a metallic container, that is electrically heated, using a voltage. And when the sample is there, it gets vaporized and atomized as well. So you can see you can use it, for solids, liquids, slurries, and so forth. Arc and spark ablation, very similar, to the glow discharge. The only difference, is where you take the two electrodes, the cathode, and then you've got the anode, and then you momentarily, bring them, into contact, and the sample, is on the cathode, for example, and you get, the sparking. So it's similar to what I explained before, only that it's operating based on the short circuiting system. Now, the other type of atomizer, that combines sample introduction and atomization is what you refer to as a laser ablation. And I think I explained it before, you just put the sample, on a platform, and you shine the laser, and the laser causes, the ablation and the atomization of your analyte. Another very specialized, type of atomizer, and equally, it can work as a sample introduction method, is what you refer to as hydride generation technique. This one is very, very specific, for certain types of elements, that react with sodium borohydride in the presence of an acid, to create volatile hydrides. And volatile hydrides, they've got fairly low vapor pressure. Rather, sorry, they've got fairly high vapor pressure, meaning that, they are fairly volatile. And because they are fairly volatile, they can just simply, after the reaction, they tend to be in the vapor phase, and you can sweep them, using an argon gas, and then you can take them, to the atomizer or to the detector, and so on. So you can see this technique, tends to be very, very selective, and very, very selective, for arsenic, antimony, things like tin, bismuth, and lead, which are the 6, types of elements that tend to form hydrides, when you do the reaction with sodium borohydride in the presence of an acid. And you can see the limits of detection are fairly low, that is 10 to 100. They are increased 10 to 100 because of the fact that it's a very selective system. So you can see matrices really, tends to be less of a problem here because you're dealing with a fairly selective type of technique. Another method of sample introduction, that is fairly specialized, is what you refer to as a cold vapor atomization technique. And this one is only very selective for mercury. Now, mercury, we all know is a very unique type of metal, because it's fairly volatile. It's got a fairly low high vapor pressure. And because of that, if you put, the sample containing mercury in a volumetric flask, for example, and then you've got argon gas, that is aerating the sample, the argon is gonna carry, the mercury vapor, into the detection system, and so on. Of course, if at all you're dealing with atomic emission spectrometer, of course, you need to heat up, the system, so that the mercury vapor, gets excited and it relaxes, to give you fluorescence, okay? And so you can see very, very specific technique, to mercury. And so if at all I give you a sample, maybe it's a water sample, often, mercury would be present, in form of iron. So you need to take that sample and reduce those ions or cations. You reduce them, into the metal, and then after that, you can, sweep it using an argon gas, into the atomizer, if at all you're dealing with AES system. Now, you can see with the cold vapor atomic fluorescence system, which is the only commercial technique actually, for atoms, you can have detection limits of up to 1 picogram. And again, it's only commercial, for mercury, because mercury has got a fairly, high vapor pressure, and so on. So let us quickly discuss, the theory, behind, atomization, or what is actually taking place. As I explained before, typically you've got a sample, and often it's a solution. Of course, you can also do liquids, as I have said. And then you nebulize it using the different types of nebulization, pneumatic nebulization techniques, that I talked about. And with nebulization, you're converting, the solution into a spray or into a mist. So the next step, is you push this mist, into the atomizer. And in the atomizer, all these steps, are actually taking place. The very first step, that happens in the atomizer is to get rid of the liquid using the process referred to as dissolution. Meaning you're gonna get, your sample, and then you remove any solvent, that is present, essentially, through vaporization, right? And so after that, you're gonna get now the molecule, in solid form. The next step, is what you refer to as, volatilization, where you take, now the molecule, that is in solid form, of course, is in very, very tiny particles, and then you convert it, into gas, of course, using very high temperatures. Now, after you have now the molecule in gas form, the next step is what you refer to as dissociation, where now you atomize or break down, those molecules into the component atoms, which are, in gaseous form. If at all you're interested, with ionization, assume your detector is a mass spectrometer. Other things, can equally happen, such as ionization. However, if at all you're doing AAS, ideally you want the process to stop at dissociation. If at all you're doing AES, again, you largely want the process, to stop, at dissociation. You do not want ionization to happen. However, if at all the detection system is a mass spec, then you want ionization, to take place. And this can equally happen, inside the atomizer. So there's a balancing act, really, between, having the temperature hot enough to cause ionization, which can be a good thing with the mass spec. But if at all you don't have a mass spec and you just have an AES system, essentially you don't want ionization. If ionization takes place, this one is a matrix effects problem. So let us talk very, very quickly, about the different types of atomizers, that are used. You guys in the lab already are familiar with the flame. And, there are different types of gases that you can use to make the flame. And depending on the type of gas that you use, you can have different types of temperatures. Ideally, of course, you are looking for the hottest temperature possible. If you guys in the lab, remember in the lab, you used acetylene and the air, as your gases. And so that was your temperature profile. As you can see, the temperatures are not too high. And as such, flames are typically used, with AAS system, okay? Because a flame is not hot enough, to really cause excitation and an emission for you to do AES. So with the flame, you typically just do the atomic absorption spectrometer, because the flame is just good enough, really, to cause atomization. Another better system, that you can use is what you refer to as a graphite furnace. Atomic graphite furnace, spectrometer. And this is where you use the electrothermal vaporization, as your atomizer. The good thing with this system, is the fact that, the furnace is very, very small. And again, you can just deposit a very small amount of sample, into the furnace, which sometimes can even be 1 microliter. Remember, when you guys did the flame AA, remember, it is very, very wasteful, of the sample. If you remember, you are using something like 10 mils of sample, per minute, so it's a very wasteful method. But with a graphite furnace, atomic spectrometer, you use a very, very tiny little furnace. And so, you can use a very small amount of the sample. And so the steps, with the graphite furnace is, you deposit the sample and then you evaporate the solvent, just by ramping up the temperature. So it operates very similar, really, to a gas chromatography. So you increase the temperature to around 100 degrees, which is the boiling point of water. And that way you vaporize, the solvent. And then after that, you can increase the temperature to around 1500 degrees centigrade. And that way you break down any organic matter that is present in the sample. And then after that, you can now atomize your sample by ramping up the temperature, to 3000 degrees centigrade. So you can see, with this system, you are able actually to remove some of the matrices that can be present in the sample. So it's a better technique, obviously, because you can improve, the limits of detection by removing the different types of matrices that are present. So very quickly, if you can compare between the flame AA and the electrothermal, and that is a graphite furnace, sometimes we'll call it a graphite furnace, AA. So again, you can see the different benefits. Say the flame, the precision is very good with the flame, and it tends to be fairly fast as well, but it's got fairly low limits of detection. It's not very, very sensitive. On the other hand, with the electrothermal type of vaporization, you can use very small amounts of sample, which is a very good thing. It is fairly sensitive compared to the flame. Unfortunately, you get poor precision, because of the different types of steps that I talked about. And the fact that, you're depositing very small amounts of sample. Anytime you use very small amounts of sample, the standard deviation, of that sample volume, is fairly high. And that impacts, your precision. So electrothermal vaporization is not as precise, compared, to the flame. And also the technique tends to be slower because of the fact that, you are doing this multi-step, temperature gradient increase. And of course, that increases the amount of time that you use to run each sample. So there are a couple of issues, that you face when you're doing spectroscopy, particularly atomic, spectroscopy. Now, remember, the very first component that we've been talking a lot about, is a light source. And as you guys well know, the typical light source that you use with atomic absorption spectroscopy is actually the hollow cathode lamp, which typically looks like that. Now, I already explained before how the hollow cathode lamp, which is a light source, I said it's just simply a cathode, that is coated with the metal of interest and is put inside, a pressurized inert gas chamber, and the gas is ionized, to produce the argon cations, which are sputter, which are accelerated to the cathode containing the sample, and you get the sputtering effect and the excitation of the element, and then it relaxes back, to give you, the lines or the light, that you are interested in. The light that you get, from a hollow cathode lamp is a line source, meaning, it's got a very, very small or well-defined discrete peak, at a certain wavelength. Unfortunately, though this is the good thing, as this light transitions, into the atomizer, unfortunately, it starts to broaden. And when it's broadening, it affects, the fact that if it's broadening, it's affecting, the detection, in the end, the limit of detection gets impacted, because of the line source, being broadened as it's transitioning, from the atomizer, to the detector. And as it's being broadened, it affects, of course, the limit, the limits of detection. So the question is, why does broadening happen? And what can you do about minimizing the broadening effect, of the light source, which ideally, should be completely monochromatic, and which otherwise, if you don't do anything about it, as I said, it impacts, your limits of detection. As you can see from my image here, so initially from the light source, the hollow cathode lamp, you've got very nicely defined peaks. as it's transitioning and being absorbed, in the atomizer, it starts to broaden. So the question is, why do you get the broadening effect? And the broadening effect, is largely because of three factors, that are at play, which I think some of which you've come across, in the chemistry 102. Now, one factor that is happening is what you refer to as a Heisenberg, uncertainty principle, meaning that it's fairly difficult, to determine the position of an electron as it's transitioning, from an excited state, to the ground state. So you cannot really, determine, the exact, position, of an electron. And because you're dealing really, with high temperature environments, essentially you're gonna get, excitation, of your atoms and so on. And so Heisenberg uncertainty principle is one factor, that actually impacts, the line source and causes, band broadening. Another factor, that causes line broadening is what you call the Doppler effect. And the Doppler effect, largely means the fact that if at all you've got, molecule or an atom in the flame, and because the flame, is fairly violent, these atom, can be moving in different kinds of directions. Okay, you got the detector right here. Okay, and so you can have some atoms, moving, towards the detector, whereas other atoms are moving, away from the detector. And also you've got, the light source here. You've got, some atoms, that are moving, towards the light source, and others are receding away from the light source. And because of that, the atoms that are going towards the light source are gonna experience higher frequencies, compared to those that are receding, from the light source. Similarly, with the detector, it is the same thing. If at all you've got atoms that are going towards the detector, again, you get some differential frequency perturbation, that is taking place. And because of that, you actually get the so-called, Doppler effect happening. Now, the last type of broadening effect, from the broadening is what you refer to as, pressure broadening. Now, if you think about it, in the flame, you would have a lot of atoms, that are present. And as light, is impinging these atoms, these atoms are equally, colliding as well. And because of that, you create, a pressure region, because of these violent, nature, of the atoms. And because of that, there's a broadening effect, of the light source. Again, because, because of the kinetic energies, of the atoms, that are different, within the flame. I hope it's fairly clear, that within the flame, typically, you've got atoms that are moving and they've got different kinetic energies. And because of that, when the light source is impinging those, atoms that have got different kinetic energies, the absorption of that light actually is gonna be fairly different, and as such, there will be a broadening effect. So hopefully it's fairly clear, again, the Heisenberg uncertainty principle is one cause of band broadening. The Doppler effect, is another cause of band broadening, again, because of differential movement, of the atoms towards the detector or towards, the light source. And also the pressure effect, because of the kinetic energies that are different, depending on the speed of the atoms, and as such, they're gonna impinge, the light using at a different frequency, and because of that, you get the band broadening. Now, there's a fourth one that I'm going to talk about it a little later. There's also what you refer to as the Zeeman effect, which is also another cause of band broadening. And this is often common if at all there's an electric field, that is close, to the light source. If at all you've got a line source and you put an electric field or even a magnet, fairly close to it, it tends to split, into other wavelengths, and that is what you refer to as the Zeeman effect. So in the next chapter, we're gonna talk about what we can do, to correct other problems that are taking place, within the spectrometer. Particularly, you've got the flame. In the flame, typically you've got, smoke that is present and so on. There are particles, that are present. If at all, again, you've got a furnace, and you're ashing something, in the furnace. Again, you've got a lot of, dust particles or smoke, that is present. And again, that can really affect the limits of detection. If at all you've got equally a plasma, you've got the very strong light, that is coming from the plasma. And again, if it ends up in the detector, that impacts your background signal. So again, how do you correct, for some of these background effects that really degrade, your signal to noise? So in the next lecture, you're going to talk about the different components, that you can integrate within the atomic spectrometers, so that you can correct, for these problems of background effects.